Hi there! Today we're continuing discussing the topic of space internetworking together with Joan Adrià Ruiz de Azua from the Nanosatellite Lab at the Universitat Politècnica de Catalunya, UPC. The Nanosatellite Lab, led by Professor Adriano Camps and the research team led by me at Skoltech, have been working together on a flight demonstration of space internetworking at the end of 2019, where we demonstrated some of the ideas of federated satellite systems flying stratospheric balloon. The project was led by Joan Adrià, who's with us today, and he's going to talk about that. He's going to talk about the flight demonstrations that he was able to put together and that we operated as a team in the Russian countryside. Thank you for your attention. Enjoy this video. Multi-layer satellite networks and mega constellations sound really interesting. However, as you know, people have been exploring other concepts of space internetworking as well, such as satellite federations. Can you tell us a bit more if those satellite networks that you have presented could benefit from, for example, federated approaches?
This is a good question. How we can use this network infrastructure for the federated approaches? We need first of all to understand one important thing. All the previous satellite networks were defined with a specific and custom satellite system architecture. Therefore, the technology developed in these architectures cannot be applied in others. I am not going to explain the concept of federated satellite system because you, Alessandro, has perfectly presented it previously. Note, however, that federated approaches are characterized by opportunistically interacting heterogeneous satellites. For that reason, it is difficult that custom and fixed solution as the previous satellite networks could match with this philosophy. In our lab, we have been thinking on this problem, and we put ourselves the following question. How these different satellite systems could communicate between them following this opportunistic nature of federations? Paradoxically, the solution was found in the current Internet on ground. Internet is composed of autonomous systems that are interconnected to construct this big and global network. We're starting to imagine satellite systems or constellations connected between them, creating sporadic networks. This is what we call the Internet of Satellites paradigm. This paradigm does not propose a solution based on having a specific custom and unique infrastructure. Indeed, it promotes the establishment of sporadic satellite networks, called inter-satellite networks. These networks are thus created opportunistically and when they are needed. This kind of network follows the nature of the federated approaches at the network level, generating temporal networks with the collaboration of intermediate nodes. These intermediate nodes establishing point-to-point federations to forward data. Let's see this chart to clarify the concept. In this scenario, three different inter-satellite networks are created because the satellite needed to interact. They will thus be destroyed when no longer are needed. You can also see that there are some nodes that can participate in multiple networks at the same time. In this context, the satellites that compose the network are totally heterogeneous nodes, with different capacities and communication capabilities. The deployment of these networks is an important technology challenge. If you are more interested in this concept of the paradigm, I recommend to read our article that you can find below.
That is challenging, right? Basically, what you're saying is that in satellite federations, we are not predefining an architecture. How can you then deploy this effectively?
Totally! Determining a route between two remote satellites and composed of intermediate nodes in this heterogeneous and sporadic network is a major challenge. Remember that satellite motion greatly impacts the network topology. The previous satellite system architectures tried to mitigate this by determining a custom architecture. Otherwise, this dynamic topology and fast environment appear, and it is the case of federated approaches. What does this dynamic environment provoke? The main phenomena that appears is the disruption of the network. It represents the fragmentation of the network in different groups of satellites, which sometimes they are connected and other times not. Therefore, we cannot ensure that a satellite is always reachable from the same source. In a previous work, we investigated if this would be a serious limitation for LEO satellite networks. In particular, satellites download data using mobile ad hoc networks technique, which are not designed for satellite networks. Although the performance was not the ideal one, we could identify time windows in which a downlink over this network was feasible. The big question remains on if it would be possible to estimate these opportunistic windows and use them. The answer is yes, because satellites follow a predictable trajectory. Before starting to talk about predictions, we have to better understand possible solutions to the network disruption. The delay and disruption tolerant networks theory have investigated how to mitigate and coexist with this phenomena. Some solutions take advantage of the satellite orbit trajectory, which is indeed deterministic. Using this determinism, it is possible to estimate when two satellites will be close enough to establish a link. In this literature, a link is called contact because it has a duration or lifetime. In this case, the route is defined over time, making a scheduling of the different contacts between the satellites. Let's watch this video to clarify the concept. Here in this video, the contacts are represented in yellow boxes, correctly scheduled from the left to the right. You can detect that the red, green, and blue data boxes are exchanged between the nodes when a contact is visible. Therefore, the route with the intermediate nodes is defined with these contacts, and thus over time. Some investigations have tried to define different mechanisms to construct this contact plan or a schedule. Traditionally, a centralized solution in which the ground facilities propagate orbit trajectories, pre-computes the contact plan, and upload it to the satellite was used. Although it can generate accurate plans for complex systems, the uploaded process of the plan needs to still be further investigated. Alternatively, new investigations aims at providing autonomy to satellite systems by enabling the capability to estimate route changes. We have been working on an autonomous and decentralized protocol by which a satellite identifies other network satellites and predicts when a contact happens. The proposed solution uses the satellite orbital elements to formulate a simple model without propagating any entire trajectory. Everything has been based on considering a contact as a satellite proximity or closeness. With this predictive model, it is possible to construct the entire contact plan and thus anticipate to the network disruption.
So, you have presented the concept of IEO-SAT using FSS and the challenges due to network disruption. How can you create federations in such a hard environment?
Before starting to talk about how, we need first to understand the nature of federations. Normally, satellites perform different tasks that consume its resources, such as power or memory. These tasks change thus the state of the resources over time. In this context, a satellite can offer its remaining resources as services that can be consumed by other satellites to perform their task. This is the federation. For instance, a satellite can offer the service to download data because it is in contact with the ground station. A service is thus offered only when it is available during a lapse of time. This temporal availability generates valuable opportunities to consume the service by the other satellites. So, we pose the question of how a satellite could notify the availability of a service. We have been working on a dissemination protocol that follows the opportunistic nature of the service. Therefore, a service is notified when it is available, and this notification is properly forwarded to the different satellites. Okay, so now that the satellite can receive the notification, how does it establish the federation to consume this service? We conceived a protocol to do that. In particular, it starts by the interested satellite requesting the corresponding service. This request is accepted by the satellite which provides the service, or maybe not. This decision depends still on the availability of the service. Once the federation is established, the service is consumed until it is no longer available. At this moment, the federation is closed.
Cool. I guess the interesting part now is to discuss how you or others have demonstrated these ideas of federations in practice. As you know, we at Skoltech have done for some years some initial demonstrations of federated concepts using software-defined radio and optical communication experiments using stratospheric balloons. At the same time, you guys at UPC came up with interesting demonstrations, and last year we decided to do something fun together. We launched a balloon mission outside of Moscow, did we?
Next time, maybe?
Yes! We catch the signal!
I am receiving as well.
Can you tell us more about this adventure and what brought you to it?
Yeah, it was a unique experience, and indeed it went well. We could retrieve a lot of results and establish some federations, thanks to the effort of both teams, the Skoltech and UPC students. Before reaching this milestone, we always start with the simulation of our protocols. Our lab has a satellite network simulator extending the Network Simulator version 3 engine. After passing these simulations and the correct performance, we jump to the hardware part. In this case of the stratospheric balloons, we implemented the FSS experiment payload. The payload was tested in a campaign with 3 stratospheric balloons. The idea was to establish federations between the balloons using the previous protocol to download data to a ground station. This chart tries to clarify the concept. The FSS experiment payload was composed of a radio frequency model to establish intersatellite links between the balloons and the different implemented protocols. Here in this image, you can see the payload inside one of the balloons. Indeed, it is the gray box there. The campaign was successful and amazing. We could establish multiple federations between the balloons and the ground station. Indeed, we could demonstrate that thanks to our approach, it was possible to download data of a balloon that was not reachable directly from the ground station. We could do this to increase the communication range using intermediate balloons. It was an amazing experience that I personally appreciate and thank. All the process, starting from the implementation of the balloons to the operation part, was amusing. I will never forget the moment to recover the balloon in the cold night. I imagine that you neither, isn't it, Alessandro?
That was indeed a great adventure together, Joan. We had the chance to do excellent science too and really demonstrate the point of federated networks in practice. Thank you so much for joining us today. Muchas gracias.
It has been a great pleasure. Hasta la próxima.